Hello, citizens, and welcome to Environmental Stuff is Hard with me, Bill Burris. This is part 2, Environmental Science is Hard. This presentation is brought to you by the Earth Forum of Howard County, one of the many missions of the First Presbyterian Church of Howard County. This is also a Christian education presentation. As a Christian education presentation, we have to have some Bible verses, so here we go. First words from Matthew chapter 22, verses 34 through 40. When the Pharisees heard that he had silenced the Sadducees, they gathered together, and one of them, a lawyer, asked him a question to test him. "Teacher, which commandment in the law is the greatest?" He said to them, "You shall love the Lord your God with all your heart, and with all your soul, and with all your mind. This is the greatest and first commandment. And the second is like it. You shall love your neighbor as yourself. On these two commandments hang all the law and the prophets." So, welcome. If you're coming to us from the Earth Forum of Howard County, welcome to the First Presbyterian Church of Howard County's YouTube channel. Feel free to look around, kick the tires, take a look at everything you want. There are several other Christian education events presented by that guy, Bill Burris. Those you should view with a little bit of suspicion, but everything else is fantastic. The much dreaded agenda for this particular presentation. We're going to have the opening prayer, some caveats and disclaimers. We're going to look at the schedule. We're going to talk a little bit about rainbows and risk, and then we're going to talk about environmental science and why environmental science is so hard. So the opening prayer, if you know it, say it with me. Dear Lord, even though Bill is teaching us, may we please learn something of value. Amen. And with that, we jump into caveats and disclaimers. Typically, I'm often arguing, hey, I don't know anything about anything that I'm talking about. Take everything I say with a grain of salt. But it turns out we're talking about environmental stuff. And Bill, that is me, is an environmental and engineering geologist, and I have actually like years and letters and names and experience and all kinds of stuff on dirt, rocks, water, and national environmental policy. So anything else is suspect. But that stuff, yeah, okay. That's stuff I might know something about. I work for the United States Air Force. In fact, I'm an environmental restoration program manager for the Air Force. So this presentation is an Air Force thing, right? Nope, wrong. This is not. I am speaking for myself. So we got to put in this caveat: opinions and viewpoints presented here do not necessarily reflect those of the Department of Defense, the Earth Forum of Howard County, or First Presbyterian Church of Howard County. Yep. Okay, this is the greatly feared schedule. This is presentation number 2, Environmental Science is Hard. I encourage you to go back and go to the first presentation, Environmental Stuff is Hard, the introduction, and the next presentation should be Environmental Politics is Hard. And we're going to veer off here onto a biblical tangent and ask, what about that rainbow promise? What rainbow promise? The one from Genesis chapter 9. Let's look at verses 13 through 17. I have set my bow in the clouds, and it shall be a sign of the covenant between me and the earth. When I bring clouds over the earth, and the bow is seen in the clouds, I will remember my covenant that is between me and you and every living creature of all flesh, and the waters shall never again become a flood to destroy all flesh. When the bow is in the clouds, I will see it and remember the everlasting covenant between God and every living creature of all flesh that is on earth. God said to Noah, this is a sign of the covenant that I have established between me and all flesh that is on the earth. So I ask, because this is my opinion, but I ask, is this a promise from God not to destroy us all with some form of natural disaster? And then if that's the case, then the next question is the same in response to Professor Leonard Palmer, who you see here pictured. He was one of my geology professors at graduate school who used to argue that there's no such thing as a natural disaster. That's what he would argue. And if that's the case, then maybe this promise might be moot. So, Dr. Palmer claims that there are no natural disasters. So when are acts of God no longer an act of God. So one of the primary acts of God, one would argue, is hitting the earth with an asteroid. But as soon as we as human beings have agency, that we have the ability to recognize, find the asteroid, and maybe do something to stop the asteroid from hitting the earth, then is it again a natural disaster? Dr. Palmer argued that there's no such thing as a natural disaster or a natural hazard, that the human component is what makes it hazardous. And so I bring to you the story of the boulder and the earthquake. And when I was living in Oregon in grad school, back in the days when dinosaurs roamed the land, and Dr. Palmer was an emeritus professor there at Portland State University, we had an earthquake. And during that earthquake, a boulder was shaken loose. It was on a Sunday morning, and the boulder shook loose, and it rolled down the hillside, and it hit a truck with a father and a daughter in it and killed them both as they were on their way to church. And this is, oh my gosh, this is an act of God. Why would God, kill this young innocent child, so on and so forth. All those kind of questions were being asked. This was an act of God. That's how everybody viewed it, except for those of us who were involved in geology and engineering and that sort of thing. Well, we didn't see this as a failure or an act of God. We saw this as a human failure, because it was human beings who built the road. No, human beings didn't necessarily put the truck there and the person there, other than the fact that we put the road there. But the road was built there. The slope was designed. The rock was allowed to remain where it was. The rockfall hazard was not adequately assessed for the seismic risk, so on and so forth. We saw this as a failing of our industry, not as an act of God. And so why am I bringing all of this up in relation to the Rainbow Promise, this promise that maybe there'll be no natural disasters that will, put us all at risk? And I argue this in terms of climate change. What about climate change? We are due potentially for some dramatic and drastic alterations, natural disasters, so to speak, related to climate change. Is that an act of God, or is that an act of humanity? And since we have some agency in recognizing the potential for climate change and some agency in causing climate change, is this an exemption, so to speak, from the Rainbow Promise? So let us take a game theory approach to climate change. This is the big topic, of environmental topic, that everybody in the world should be knocking their heads against. Is it right here, climate change. This is one of the hard topics that we should be dealing with. All right. And one of the first issues that we have to wrestle with is climate change real, or is climate change fake? And so I would like you to consider a game theory approach to climate change, whether or not it's real or if it's fake, and if it's whether or not we take action. And it's actually quite broken down into 4 simple things. If it's real and we take action, then the effort we spent was well spent. And if it's fake and we take action, then the effort is wasted. If climate change is real and we fail to take action, then there's potential for enormous disaster. Whereas if it's fake and we don't take action, then we have not wasted money. So that's the breakdown. It's really quite simple. Is it real or is it fake? Do you take action or not take action? And then you have to start doing a risk-reward analysis. Is it worth the risk of wasting effort to prevent this enormous disaster? So now let's go to the wonderful world of risk management. What I'm showing before you is a conventional risk management table. This is used by risk management professionals throughout the entire world in all kinds of industry, including, I might add, the United States Air Force, where we do operational risk management for mission activities on an active airfield. And you start to, it says a qualitative risk management matrix where you look at the impact. You have little to no impact, some impact, or high impact. And in case of the Air Force, we would call high impact death or failure of the mission. And then at the bottom, you have probability, the likelihood that an event will occur. Is it not likely, somewhat likely, or very likely? And so the concept is that if you're going to have a potential high impact, if something goes wrong, it's going to be disastrous, and it's very likely to occur, that is a critical risk and it needs to be addressed. And you work your way down from critical to high to medium to low. So I think we can all agree that if climate change is real, that the impact that climate change is going to have is very high. And then from there, you have to decide, is it not likely to occur, aka fake? Or is it very likely to occur, very real and it's going to happen? So by the standards of conventional risk management, even if you think climate change is unlikely to occur, the risk is still high. By conventional risk management, this matrix I'm showing you is conventional risk management used by risk managers throughout the world, throughout all industry. If you take a look at it, say it's very low probability. Even if you make that argument that there's a low probability of climate change, the impact of that climate change is high, and as a result, the overall risk is high. And so it warrants activity, it warrants action. Which leads us to environmental science, and why environmental science is so hard. So again, environmental science includes chemistry and physics, biology, toxicology, ecology, geology, hydrology, hydrogeology, meteorology, climate science. Just about everything seems to mix into this giant mix that we call environmental science. And you got to add into that environmental engineering, natural resource management, agricultural sciences have an impact on environmental science, and just about any other thing that you can think of. And what is really strange, though, is despite the enormous complexity of environmental science, at least at an undergraduate level, environmental science is kind of considered by the academic world as the light science option. Because when you take environmental science classes, you take a little bit basic chemistry, you take a little bit of basic biology, you take a little bit of basic geology, so on and so forth. But you don't delve deep into any one of those topics, and then you throw on some classes on top of it that maybe are specific to some realm of environmental science. Maybe you learn a little bit more about forestry or trees or something, but it's considered to be kind of the lighter, less hard science to study, at least at an undergraduate level. And I always found that very interesting. Because as I've progressed through my career, and my undergraduate background was geology, and I looked down with a certain degree of disdain on environmental science as an academic study. And now, as the years have gone by, I think that's unfair to look at environmental science through that lens. On the other hand, I don't think we're training our environmental scientists at an undergraduate level with the rigor that's required to address some of the enormous challenges and complexities that are encapsulated within environmental science. So, environmental science is one of the hardest sciences due to its enormous complexity. And for an example, let's go right back to climate change. You may very well ask, what is complex about climate change? The facts are quite simple. Carbon dioxide is a greenhouse gas. The more carbon dioxide that you release into the atmosphere, the more it is going to envelop the earth and capture the heat from the sun and not allow it to go back out into space. You can prove in laboratory testing very easily that CO2 is a gas that retains heat. It serves as an insulator, almost like a blanket that covers the earth and holds in heat. Human activity is a significant driver in CO2 emissions. Every time I get in my car and I drive down the road, I am taking gasoline, a complex mixture of hydrogen and carbon, and I am burning it, that is oxidizing it and turning it in the hydrogen into water, hydrogen and oxygen, H2O, and all the carbon into CO2, carbon dioxide, and as a result I am emitting carbon dioxide into the atmosphere. And we know that we're emitting a lot of carbon dioxide into the atmosphere because the fossil fuel industry tells us how much we burn each year during their earnings calls. We sold X amount of millions of gallons of gasoline, and presumably we all burned that stuff somewhere, someplace in the world. Greenhouse gases such as CO2 result in climate change, aka what we all call or used to call global warming. But it turns out that climate change is far more complex. It's a combination of many, many factors. Chemistry, for example. Right off the bat, I talked about we know how much CO2 is being released in the atmosphere through the burning of petroleum. Now here's the disconnect. When you read how much petroleum we are releasing via burning of fossil fuels, we should expect to see more in the atmosphere than we actually do. So where is the remaining carbon going? Well, maybe some of it is going to plants. Maybe some of it's going to animals. Or maybe it's being dissolved and acidifying or increasing the pH of the oceans. There's atmospheric physics, the mixing of stuff in the atmosphere, and how much impact that has on CO2 levels and so on and so forth. The weather, meteorology, geology, volcanology, both of which have an impact on CO2 emissions because human beings aren't the only emitters of carbon dioxide. Volcanoes emit carbon dioxide, and a lot during large volcanic events. And paleontology, when we go through the fossil record, we see that climate change has been a long occurring something that's happened in the past many, many times. And human beings weren't around to cause those climate change events. Then you have ecology, biology, plant uptake of carbon dioxide, so on and so forth. Oceanography, the ocean sucking up, being a sink for carbon dioxide. But when you take a look at all of these various factors, most of them are not positive. For example, biology, plants. We think of, oh, plants are uptaking carbon dioxide. That's good for plants. But then when you actually start looking at how much plant mass, biomass that is currently existing on the earth, we're wiping out our major biomasses, aka rainforests and things along that line. We're actually adding more carbon and destroying carbon sinks, things that. So when you look at most of these factors, most of them are not what we would regard as positive changes. Having the ocean absorb carbon dioxide and therefore become more acidic is not a positive change. Then to add to all of that, trying to understand and communicate to the world at large the science, bad science, and good science. So one of the common mechanisms that's used is this correlation between CO2 concentration in the atmosphere and climate change. When you take the two graphs and you overlap them, it's, oh, isn't that interesting? This is evidence that climate change, yes. The evidence for climate change is that we know that CO2 concentration, as it increases, we expect it to also result in global climate change and global warming. But you can't just slap a line on a graph and say, oh, look at this interesting correlation. So for example, this I would argue is bad science. So here's another example. What about this graph? This is global climate versus the number of pirates. Okay, average global climate change temperature is in red. The number of pirates approximate on the planet is in blue. And since we've wiped out pirates, climate change has gone up. And as a result, what we should be doing is increasing piracy. So my point is this, is that you're taking a correlation. Now, the major difference between CO2 correlation and climate change is that at least you can causally link the two together, where it's much harder to causally link pirates to temperature. The other thing that we often use are predictions and models. Let's look at all of these models. These models say that we're due for major climate change, and yet often models don't match observations. Here's a primary example where one of the various models indicates that here we are at 2020, we should be cranking up much, much higher climate change than we've actually observed. And that just indicates, again, the complexity of all of the factors that are involved in climate change, and that not necessarily all of those factors are being accounted for in the climate models that were being run at this time. So maybe you're going to take what I just said and start inferring that Bill, the environmental expert, is arguing that climate change is not occurring, and that's not the case at all. By every measure of scientific measurement, climate change is occurring, and the trend is negative. Global temperatures are rising. It is hard to determine how much of climate change is a result of human activity, and it's hard to determine how much worse it will get. But it is very difficult, in my opinion, to argue that we don't have some agency in the increase in climate change. And the potential for the results to be disastrous, to have a high impact, is what should be driving our decision making, which brings us back to the risk stuff that I mentioned previously. So I'm now going to use that as a bad segue into the next topic, or the next example, why environmental stuff is hard, and this is the issue of risk. We're going to talk about what I feel is the epitome of complex, that is hard environmental science, and that is PFOS and PFOA, which I would argue is currently the largest non-climate related environmental issue facing us as a nation. And I'm electing to discuss it here because it is super duper complex, super challenging, super hard to deal with, and because I live and breathe this stuff almost on a daily basis as an environmental manager with the Department of Defense. So what is PFOS and PFOA? PFOS is, I'm only going to say this a few times because I have a hard time saying them, perfluorooctane sulfonate and perfluorooctanoic acid, both of which are components of aqueous film-forming foam, also known as AFFF, which has been used since the 1970s by the United States Air Force, the United States Navy, the aviation industry as a whole, for fighting fires. Now, welcome to the PFC alphabet soup. PFOS and PFOA are two particular compounds in a class of chemicals that are referred to as per and polyfluoroalkyl substances. So you often hear people refer to those as PFAS, P-F-A-S. And PFOS, in turn, are part of a larger family of compounds known as perfluorinated compounds, or PFCs. And other people use the term PFCs, and they often will refer to them as perfluorinated chemicals, perfluorochemicals, perfluoroalkyls, perfluorinated alkyl acids, perfluorinated so on and so forth, and goes on. Here's the thing. These are chemicals that involve carbon and fluorine. PFOS and PFOA, like all other PFCs are organic compounds because they have the carbon in there, and they are synthetic. They are not found in nature. They are only produced by us, human beings, using specific industrial chemical processes. Of all of the thousands and thousands of perfluorinated compounds out there, PFOS and PFOA are the only two that the EPA has established health advisories for drinking water. We'll get to some of that in a minute. So, PFOS, PFOA have here. Let me get out my little handy dandy little writing tool here, see if this works out. There we go. Consists of carbon chains. These are the carbon molecules, each of which is bonded next to a fluorine, 2 fluorines per carbon. And these chains can go on and on and on. So folks who discuss this will talk about C8 chains. That means 1, 2, 3, 4, 5, 6, 7, 8 carbons. You can have C4 chains with only 4 carbons, C6 chains, 6 carbons, C10 chains with 10 carbons, so on and so forth. And so that's why there are actually hundreds and hundreds of different types of perfluorinated compounds, because the sizes of these chains, every time you change the size of the chain, you're dealing with a new compound. And then in addition, you have this last carbon on the end of either the C8 or the C6 or the C4 change. Then you have different ions that tag on to the end. So PFOA has this oxygen and this OH, and then the sulfate here on our perfluorooctasulfonic acid. The PFOS, darn it, doing it again. We love PFCs. These synthetic compounds have very unique chemical properties. One is they're very stable and persistent in the environment. They are extremely stable and persistent in the environment because that chemical bond between the fluorine and the compound is the strongest chemical bond you could possibly have, and it takes an enormous amount of energy to break that bond and separate the fluorine from the carbon. So that's one reason why we like them. One of the reasons we use these in firefighting chemicals is because low temperature fires cannot break the bond between the carbon and the fluorine. It doesn't oxidize. As a result, PFCs are often used in flame retardants, as in the jammies that you get for your little kids, because you don't want your little children to turn into candles when the acrylic lights on fire. So they're often coated with PFCs to prevent your children from melding with their burning mass of acrylic jammies. They are lipid repellent. They repel fats, and they're water repellent. So stain removers, or stain repellents, not removers, but repellents, such as the Teflon Scotch Guard. You used to put Scotch Guard on everything to keep stuff from getting stained. Those are PFCs. The lipid or the fat repellent properties. We use those in non-stick cookware because we want to get stuff doesn't stick. And because these materials are stable and persistent and heat resistant, and there's very few things in the environment that break them down, they bioaccumulate. So if you get a little bit of PFOS in the little tiny critters, they move up the food chain and accumulate in the bigger critters and so on and so forth. This became a major issue when we started noticing elevated levels of perfluorinated compounds within the blood of polar bears. So we've used these a lot. Right now, we're because of the concerns, the environmental concerns, their use has been drastically curtailed. They're no longer allowed to be used in French fry boxes and things along that line. But still, we use many, many products, and as a result, they're pervasive in the environment. And guess what? All of us have got some PFCs within our bodies right now. It's almost unavoidable in our modern world. PFC-based aqueous film-forming foam, that is AFFF, has been the product of choice for fighting fires in the aviation industry since the late 1960s. In fact, it was developed as a result of a drastic, dramatic, tragic fire. Over 170 people died in a U.S. aircraft carrier fire event during the Vietnam War. And that accidental fire, they couldn't get it out in time, and all these airmen died. We need something that puts out fires really quick. And it turns out this stuff puts out fires really quick. And if you're going to use this stuff to put out fires, you want to be able to train with it. So we have been using AFFF for decades for putting out fires and for training to put out fires. Now we have converted our AFFF stocks to using film-forming foam that does not contain PFOS and PFOA. However, they do contain perfluorinated compounds, just different kinds that are not regulated. Why AFFF? Because it really, really works. It puts out fires fast. It forms a foam blanket that floats on top of the fuel, actually cuts off and absorbs oxygen, cuts off the oxygen supply from the fire, and very, very quickly puts it out. So how toxic is this stuff? So toxic that the EPA's got to put out this advisory level. And the question is, well, that's a hard question to answer. We don't have an answer. And in fact, that's one of the reasons why dealing with PFOS, PFOA is so darn hard. It's because the toxicology is hard to get a handle on. The studies that we have conducted show that PFOS, PFOA may be associated with certain developmental delays in fetuses and children. There have been noted decreases in fertility, increased cholesterol, alterations in immune system, increased immune system deficiency, things along that line, changes in liver enzyme, prostate, kidney, increase in testicular cancer, so on and so forth. But all of these studies are based upon epidemiological analysis of exposed populations to PFOS, PFOA, mostly at locations where PFOS, PFOA are produced. So either the factory workers at plants that make these various substances or the surrounding population who've been exposed to these substances at elevated and higher levels. And we have not been able to establish a direct causal link, how these materials actually cause these various chronic health conditions, nor how substantial or severe these health conditions are as a result of exposure to for example, elevated cholesterol levels. Elevated cholesterol levels, well, a lot of these plants are in Minnesota. How many people are eating a lot of lutefisk? All I'm saying is that we have not been able successfully to establish the links and cause between PFOS, PFOA exposure and the health effects. What about the lab rats? What do they say? Conventional toxicology you take rats and you dose them up with the various compounds of concern, and you start noticing when it starts killing them or giving them cancer. And I don't have enough time here to start actually going through traditional toxicology. and how, this different weights of concentrations to the weights of the rats and the curves and threshold levels, things along that. We're going to set that all aside for a moment. In terms of perfluora, PFOS and PFOA and that sort of stuff like that, traditional, or should I say conventional laboratory testing with animals has not been working to help establish any kind of potential risks, because it is apparent that laboratory animals respond differently to PFOS, PFOA than human beings, especially rodents. They're able to cycle out this material, something about their systems and their metabolism. They're able to cycle out this material and expel it from their bodies much quicker than human beings. So I'm going to read this quotation. This is from an article from a National Institute of Health publication. The tremendous variation in the speed with which humans and laboratory animals can eliminate PFOA is one example of why understanding how the compounds are processed in the body poses such a formidable challenge. You can go from hours for a female rat to days for a male rat to months for a monkey to almost 4 years in humans, explains Jennifer Seed Branch, Chief EPA Toxicology Prevention and Toxics. My point is that traditional, I shouldn't use that word, conventional toxicology and laboratory testing of rats does not give us the answers that we need to determine the risks associated with PFOS and PFOA exposure in human beings. And as a result, we're relying upon epidemiological studies. Nevertheless, in a controversial decision, and some, like myself, would argue that should not necessarily have done this. This was not ready for prime time, so to speak. The science doesn't back it up. But nevertheless, in 2016, the EPA issued a lifetime health advisory for PFOS and PFOA. This is not a regulation. It is an advisory of 70 parts per trillion. So you take the two compounds, you add them together, and you shouldn't have any more than 70 parts per trillion in your drinking water. And the lifetime health advisory means that the idea is that you're going to be consuming this water for at least 30 years. So if you're going to be drinking from this water source for 30 years, then you should be trying to make sure that the PFOS and PFOA levels in that water are below 70 parts per trillion. They're only guidance. They're not regulations. They're not a requirement. You have to go through a whole regulatory process if you're going to develop a true regulation, which the EPA is now working its way through doing. And this health advisory information is now commonly used to determine risk in the cleanup of water, groundwater, where you know it's been exposed. You see PFOS, PFOA in the groundwater as a result of fire training at an Air Force base like Joint Base Andrews, where I work. Well, Superfund would then say, well, you got to clean that up to below 70 parts per trillion. So the regulatory status, CERCLA, that is Superfund, the world I work in, it is not yet considered a contaminant of concern, although that's coming soon. It is not a hazardous waste and defined as such under our hazardous waste laws, known as the Resource Conservation and Recovery Act, or RCRA. It is, under the Safe Drinking Water Act, unregulated, but with the advisory level that I just mentioned of 70 parts per trillion. The Tier 3 toxicity values, which is what will, when they get finalized, which will launch it into the world of CERCLA, is what will eventually, when they get finalized, will start making this an issue under the Superfund laws. So the feds have, in a sense, at this time, not yet established any real regulatory status that you can hang your hat on. So what about the states? Many states concerned that this is an issue that the EPA has failed to address have established their own state standards for drinking water. many of which are equivalent to the EPA lifetime health advisory level of 70 parts per trillion, and many of which are even lower, and sometimes much lower, such as New Jersey, which is working at something along the line of 10 parts per trillion for PFOS and 14 parts per trillion for PFOA. Now, one of the problems that we deal with PFOS, PFOA, is the public perception when I start talking about parts per trillion. So, the maximum contaminant level for benzene in drinking water is 5 parts per billion. Mercury is 2 parts per billion. Arsenic is 100 parts per billion. And yet the lifetime health advisory level for PFOS, PFOA is 70 parts per trillion. That is several factors of 10 lower. In other words, it's lower for PFOS, PFOA than mercury. And what does that mean to a member of the public? Well, that tells a member of the public, oh my gosh, this stuff must be super duper toxic. The slightest touch of this stuff and boom, I'm dead. So here is, I believe this is at Dover, a huge poisonous mass then, a giant unloading of foam from a hangar where an accidental release of foam has occurred. The deluge system has gone off, inadvertently lightning strikes, something else had occurred, electrical malfunction, and boom, the hangar's just been dumped and filled with foam. That means that this airman right here, who's trying to figure out how to get rid of this foam, he's going to keel over dead any minute, right? Now, that lifetime health advisory level is based off of toxicology equations that we use, and it's based off of a 30-year exposure, not a single exposure event. Now, add to this public perception the issue of lawsuits, which are starting to, class action lawsuits are being built all the time. My cohort over at Dover Air Force Base said her life suddenly changed in late night television. She was sitting in bed watching, who knows, somebody on some and then suddenly, are you living near Dover Air Force Base? Are you drinking groundwater that has been impacted by foam from a Dover Air Force Base? Then call the law offices of, oh boy, here we go. So now we have all these lawsuits. And there's an enormous political response. As the outcry of the public comes out, there are enormous amount of interest in perfluorinated chemicals, especially PFOS, PFOA, and firefighting foam in the DoD coming out of Congress. Government Accountability Office, so on and so forth. New Hampshire senators want EPA to allow us. It's a big deal. This is a big, giant political issue. So you've created a very challenging public space for us. It's very challenging for the DoD to deal with PFOS and PFOA in a public space where the communication is the slightest drop of this stuff is super duper toxic and poisonous, which isn't necessarily the case. That the stuff is going to kill lots of people, which isn't the case. That the stuff is poisonous, this stuff is toxic, when the toxicity has not necessarily been established, the mechanisms of how this stuff is toxic. You're looking at epidemiological and not traditional studies. And yet the DoD is wrestling with all of the political and public outcry implications as they try to manage this particular issue moving forward. And it is not easy. So some of the basic challenges that we face in dealing with PFOS, PFOA is right at the start. The EPA issues in 2016 a lifetime health advisory level saying 70 parts per trillion PFOS, PFOA, but the EPA didn't have a laboratory method established on how to analyze PFOS, PFOA at those levels. So one of the major issues, that challenges, it's since been overcome, but one of the first challenges that we faced as an industry is how do you set a standard, a laboratory standard to measure against at 70 parts per trillion. This is microscopically small. 70 parts per trillion is almost impossibly small. How do you actually say, oh, this is the standard. I know this is exactly 70 parts per trillion. That's how you analyze stuff, is you compare it to a standard. It's almost like you start at the very start of the run of your laboratory run, you put in a sample of your standard and say, this is what all the results are going to compare to. Here's the 70 parts per trillion chunk. You put it in, you run it, and then the machine spits out a number. I don't know. For the sake of argument, we'll say 7. So 70 equals 7, and later on the next run says 6, 10, 12, 15. You have a standard to measure against. So we've since established and developed laboratory standards, but that was one of the first major hurdles that we had to deal with. How do you set up a standard, a substance, a vial of water that you can say with a great deal of assurance, this contains 70 parts per trillion PFOS, PFOA. And again, the EPA had to actually develop a method, and they didn't actually develop a method for testing drinking water for PFOS, PFOA until 2018. That's almost 2 years after they issued their lifetime health advisory level. The DoD, because we were under such enormous pressure, actually developed laboratory methods before the EPA did on doing analysis for PFOS, PFOA. Now, the next issue. What are you going to do to treat, to filtration? You've got PFOS, PFOA in your water supply. How are you going to fix it? Well, it turns out that PFOS, PFOA can only be removed. The only effective treatment that we have right now is through granular activated carbon, and it isn't even all that effective. It doesn't take long before granular activated carbon needs to be recharged, redone, regenerated. So you pull out a canister of activated carbon, you swap it out with a new one, and you're getting relatively PFOS, PFOA free stuff coming out of the other end of this filter system. Now you got this granular activated carbon, and it's loaded with PFOS, PFOA that you've stripped out from the water. What do you do with that? Remember, this PFOS, PFOA is very hard to break down. What about all of the AFFF that you remove from the trucks and the hangars that you're not supposed to use anymore? The Air Force has removed all of their stocks of AFFF that contain PFOS, PFOA from their trucks, and are currently working to remove them all from their hangar systems, their deluge systems in the hangars. What do you do with this stuff? Well, the answer is right now, because we have no other alternative really, is you burn it in a high temperature hazardous waste incinerator at enormous expense. Now, I'm not a chemist, I'm a geologist. I have some understanding of chemistry and some understanding of how chemical analysis are conducted. I actually have some experience with gas chromatography, a standard environmental laboratory method used to deal with and analyze for very specific and kind of standard, dare I say, even traditional contamination like gasoline and solvents and things along that line. PFOS, PFOA analysis is conducted through a technique called liquid chromatography, which I know very little about, but I am told by chemists that it's hard, it's challenging, it's difficult, especially at the parts per trillion level, because many of these perfluorinated compounds are very similar, And as a result, when you're trying to analyze for PFOS and PFOA, you might start getting results from other perfluorinated compounds that are similar in structure and molecular weight. I am told that there are no machines specifically built for PFOS, PFOA analysis, that a laboratory has to order a liquid chromatography analysis machine and then open it up and strip out all of the Teflon components that are built into the machine for standard liquid chromatography analysis and replace them with other components, because the Teflon within the machine itself can result in false positives in your sample results. And these kind of pervasiveness of perfluorinated compounds in so many of the products we use, and the potential for them to result in false positives, to contaminate your sample. You're collecting a sample of groundwater from a well out in the field. Well, what happens if you're wearing a Gore-Tex coat? And the Gore-Tex has perfluorinated compounds in them that get into your sample. And as a result, you end up with a false. It doesn't take much to get a hit at 70 parts per trillion. It's just, so these are some of the many issues that we wrestle with. How do you set yourself up and collect your samples without cross-contaminating your sample? Making sure you don't result in a false positive. Now, we've already done some studies, epidemiological studies, based on populations and their exposure to PFOS and PFOA and perfluorinated compounds from these various locations where PFOS, PFOA are being made in plants and so on and so forth. But as we have some understanding, we're finding perfluorinated compounds in the blood of polar bears and other apex predators, so on and so forth. We know this stuff bioaccumulates, but we have very little understanding of the ecological risk, how PFOS, PFOA impacts ecological systems. For example, we know that we have PFOS, PFOA in the streams that are leaving Joint Base Andrews, where I'm working. Now, nobody is drinking that water, so I'm not concerned about that as a source of risk to human health and safety, but we have very poor understanding as to what kind of impact that PFOS, PFOA is having on the bugs and the critters that live in the stream, and in turn, what kind of impact that's having on the food chain, including possibly human beings who are consuming fish from the creeks that are sourced at Joint Base Andrews. Many of these issues kind of culminate into major problems for the Department of Defense. So somebody like myself who's dealing with contamination in groundwater, I've got to start arguing how clean is clean. At what level do I consider PFOS, PFOA to be a problem, and at what level do I not consider it a problem? Usually those numbers are driven by risk, but as we've noted before, it's very hard to figure out what the risk is associated, at least quantitatively, for PFOS, PFOA. Can the field and laboratory methods that we generate accurately analyze all the way down to 70 parts per trillion? Can we actually tell if you're finding this kind of contamination in locations in, for example, fish in the streams, if it's coming from the DoD, or is it coming from one of the many other myriad sources for perfluorinated compounds? For example, other fire training facilities like your local fire department. What about the regulatory status or the lack thereof at the state level and at the federal level? And how does that impact somebody like me who's trying to manage PFOS, PFOA as an issue, as an impact to public health, and bluntly as an impact to public perception? Remember, I'm trying to use environmental justice as a theme to carry through all these presentations, so I have to ask, where does environmental justice figure into this mess? And I'm not sure I have any real easy answers. just keep in mind that as we deal with PFOS, PFOA, it may have an impact on people's jobs, especially those communities that are dependent upon the factories and plants that produce this material, land and housing, areas that have been impacted by PFOS, PFOA exposure. And a major issue for marginalized communities is scientific literacy. It's much harder for us to communicate the issues surrounding perfluorinated compounds to those who are just simply not dealing with the same level of education that others have when addressing this issue. The lower levels of education that you tend to find in marginalized communities. I argue that one of the greatest challenges as a result of PFOS, PFOA, and all the complexities that are included in the environmental science addressing PFOS, PFOA is effective communication and how to communicate with the public, with regulators, with government officials, with folks within the industry, folks outside the industry, about all of the complexities that are dealing with PFOS, PFOA. So I reach back to the Bible. Here's 2 Timothy chapter 2, verses 14 through 17. Remind them of these things and charge them before God not to quarrel about words, which does no good, but only ruins the hearers. Do your best to present yourself to God as one approved, a worker who has no need to be ashamed, rightly handling the word of truth. But avoid irreverent babble, for it will lead people into more and more ungodliness, and their talk will spread like gangrene. So, to summarize for PFOS, PFOA, the chemistry is hard. The toxicology is hard. The treatment and engineering to fix it is hard. And the communication and the politics surrounding the issue are hard. Or maybe it isn't so hard. My PFOS, PFOA message now that I deal with in a professional capacity has actually been boiled down to very simplicity itself. If you put down 2 glasses of water and told me one had PFOS, PFOA in it at 70 parts per trillion, the lifetime health advisory level, and another glass of water and said that had no PFOS, PFOA in it, which would you rather drink? The answer is I'd rather drink from the glass with no PFOS, PFOA in it. And so maybe that right there is the simple goal. Let's try to drink from the water that has no PFOS, PFOA in it. How we get there, that may be the big challenge. This leads all very nicely into the next presentation's topic, environmental politics is hard. Until then, here's a picture of a praying polar bear learning not to worry. Take care.